So I'm waiting for John. Please confirm that you're able to hear. Nderito, naweza nisikia?
Yes. yes.
Okay. Then that's fine, because now I think I'm in a better position because I'm not receiving any echo. So I think now we are now doing better.
Yeah, no echoes.
Okay, then. So the session starts at 9:30. So we are now 10 minutes late. So we just continue as others join us. So we were talking about the knowledge cycle and what it is about. You said perception is about agents being able to detect the environment. All right. And learning is the ability of an agent to deduce new knowledge from what it learns. Like, just as I've given you a situation that when it sees a line, a white line between two lanes, or between a road, in the middle of a road, it should know that that is a separator, a lane separator. But then if it gets to a point where it sees a yellow line still at the middle, it needs to be able to also know that it's also still a lane separator. So learning is the ability to deduce new knowledge from the knowledge it already has. Then if an agent is able to perceive, then its environment, then we must now represent or give it knowledge so that we can tell it what to do when it perceives that. Okay, so knowledge representation is now there. It's now inducing knowledge into a system or a machine so that it can be able to perform specific actions from what it perceives in its environment. Like using its infrared sensors, it senses a barrier or another car in front of it. But what should it do? Without knowledge, that self-driving car can hit the car in front of it because it doesn't know better. It doesn't have knowledge. All right. It's like a child. When a child is small, you realize that they are able to perceive that if they go to the kitchen, they're able to see. All right, the environment. They're able to see that is a hot sufuria, that is a hot serving spoon, that is a hot jiko, and those kinds of things. But they will still go and touch it, right, and harm themselves. Why? Because they do not have knowledge about it. All right, they don't know what to do based on what they have perceived. They have seen a hot sufuria, but they don't know the right actions, the appropriate action to take when they have seen it. Okay, so if it is a car, you implant it with infrared sensors, you implant it with all those things. But if it sees a car, it can do nothing. It has just seen a car. It has seen a barrier using its cameras and all those, but it cannot do anything. Why? Because it does not have knowledge. So that's where knowledge representation comes in. You give that machine data, and what that data does, it guides the machine on what appropriate actions to take based on what it has seen, based on what it has heard, based on what it has perceived. All right, so that is where knowledge representation comes in. And then learning only happens from where? From the knowledge. Okay, learning only happens from the knowledge. That's why you see there's this arrow here. Okay, learning only happens from the knowledge. Learning only happens from the knowledge. Okay, and after, if the machine, if you give it knowledge, then that is KR, then you advance to KRR, reasoning, knowledge representation and reasoning. So reasoning is now the ability of interpolating the knowledge it has in order to perform some sets of actions. Okay, interpolating the knowledge. Reasoning is the ability to analyze the knowledge you have. So if I tell you calculate A, solve the following problem. A is equals to X plus C. And then I tell you X is equals to 2 and C is equals to X plus 3. Right? So you're able now to calculate A. Now you're able to use the knowledge you have to reason out, all right, to determine those relationships and also to come up with a logical conclusion. So reasoning is basically using the knowledge, as we have said before, using the knowledge that you have, that the agent has to do it, to basically perform some particular actions. And therefore, planning. Now, what is planning? Planning is arranging the sets of solutions in a particular order, which now the agent can pick from. Okay? Because do you remember in search, now this is where search algorithms come in. And we discussed informed search algorithms and uninformed search algorithms. So that's where the search techniques come in. They come in this area of planning. Planning is basically there are sets of solutions that it has created in this particular problem or in this particular reasoning or in previous reasonings. Okay, and there are sets of solutions that have already been determined for that particular or related actions. So now it searches through the search space. You remember the concept of search space. It searches through the nodes, looking through the nodes, through the different paths, looking for the different solutions, most optimal solutions for this particular problem. And then it ends with execution. Sorry about this, it's not education. It is execution. Execution now is the real action it takes, the real action it picks from the other actions that are in the search space, or from the other solutions that are in the search space. Okay. So for instance, a machine can have 100 things to do. That is why that's why we normally conclude that machines, there is no problem that a machine cannot solve, because it always has different ways of solving that problem based on different circumstances, that it encountered in the past, and based on the current problem that it is encountering now. That is why we can also be able to conclude that self-driving cars are safer than a what? Than a driver. All right, self-driving cars are safer than conventional cars driven by a human driver. Why? Because a human driver may panic when another car comes, right? But in that particular situation, when it is overtaken and another car is proceeding at a very high speed towards it and it's already overtaking, that self-driving car has already very many ways of solving that problem, because it calculates, it has calculated many instances, many probabilities, distances, speed, acceleration speed, deceleration speed. So basically it doesn't have emotion, so it won't panic. You know, most accidents drivers get vehicles into is not really because they didn't know what to do at that particular action. They knew, but they panicked. So their emotion took a toll of them. All right. But machines never panic, right? They never panic. Machines calculate. Machines are not emotional. They calculate. If they have a solution, they will give a solution. If they don't have a solution, they will not give a solution. They are not emotional about how they execute their tasks. That's why we can say that self-driving cars are safer. At the event of an emergency, they won't panic. They will calculate solutions, come up with 1,000 different solutions and pick the one which is most optimal. And that's why we talked about a search algorithm. One of the concepts of one of the things that make a search algorithm a best fit for a particular agent is the speed of search. You remember that? The speed of search. So if the speed is optimal, the speed is high, then we can actually be able to say that self-driving car in an emergency situation will not find it difficult to find an optimal solution for that particular emergency situation. Okay, so basically that is execution. Execution is about bringing what you picking the solution you have determined that it is the most optimal, It will maximize on the performance measure. Now bringing it to bear upon the situation or the circumstances the agent is facing at that moment. Okay, so that is what you call knowledge cycle. So remember, the first thing is to perceive, and that one is by doing what? By giving the agent some sensors that it can use. For instance, if it's a self-driving car, some infrared sensors or some cameras. Okay, then yes, it is able to see its environment, but the other problem is it does not know what to do with what it sees. It's just a camera that is able to see, that's it. It does not know what to do. So you have now to program. You have to induce knowledge. Okay, you have to induce knowledge, structural knowledge, heuristic knowledge. You have to induce meta knowledge. You have to induce all those kinds of knowledge. So you give it knowledge so that now when it sees whatever, it is able to know what it is, and it is able to know what to do when it sees that. Okay, so knowledge is what helps it to do some things when it perceives some certain things in its environment. Then through its knowledge and its experiences, through its knowledge and its experiences, as it tries to reason out different problems, then it is able to learn. Okay, so learning is not independent from knowledge or from KRR. KRR is the basis for learning. All right, if a machine has knowledge and it is able to reason, then it is able to make inferences or conclusions from new situations it faces. All right, that is why when you are learning, when we are giving you education or knowledge, you are able to face new problems in the industry. That's why what we give you is just basic knowledge. Like right now, if I'm teaching you AI, I'm giving you very basic knowledge. But if you go to the degree level or the master's level, you'll find that you now are able to use this kind of knowledge I've given you to solve new problems that you encounter in this particular area, because you have base knowledge. Okay, so that is basically why there is KRR. KRR is the platform for learning. Okay, so you cannot learn if you cram. You have to have that knowledge, and you must be able to reason it. You must be able to reason out what you are being taught. All right, and then by reasoning, you are able to meet new situations, new challenges, and face them. And that is basically learning. And of course, when a machine reasons, it plans, and that planning is basically looking for optimal solutions, the best solution in its search space. Okay, and then execution, not education, but execution. Execution, this is now where it picks on the optimal solution and brings it to bear upon the environment or upon that particular problem using what? Actuators. Okay, so that's how that is what we call the AI knowledge cycle, or what we call the knowledge representation cycle. Knowledge representation cycle or knowledge cycle, same thing. Now let's discuss the approaches of knowledge representation. The approaches of knowledge representation, what we call knowledge representation formalisms, the approaches of knowledge representation. Now, there are four main approaches of knowledge representation. In other words, and basically, just before we begin, these knowledge representation schemes or knowledge representation formalisms are informed from the types of knowledge. All right, so there are four ways of representing knowledge, and the four ways of representing knowledge are basically from the four types of knowledge, or of the five types of knowledge. So there is what we call logical representation. That's one of the representation schemes or representation formalisms. There's semantic network representation, frame representation, and product rules or production rules representation. Now, what is logical representation? Logical representation is representing rules of actions that guide the machine on what to do. representing rules of actions. And what were rules? Rules fell in what kind of knowledge? In procedural knowledge, yeah? Rules. So logical representation is basically in representing procedural knowledge, rules of actions, okay? Rules of actions. Now, basically, rules are basically logical statements, and those logical statements can be syntax or semantics. Syntax statements or syntax representations or semantic statements. Now, syntax are basically the rules which decide how we can construct sentences, appropriate sentences, given a particular situation. A syntax is a rule on how we can construct appropriate sentences given a situation. So it determines which symbol we can use and also how to write those symbols. So basically in a syntax is something like A is greater than B, therefore A is a car or a lorry. If it's a self-driving car, A is greater than B by size, therefore A is a lorry, or A is a bus, or A is a truck. A has the following parameters: length this, width this, height this, therefore A is a bus. A equal to bus. In other words, basically a logical representation in terms of syntax is basically statements, okay? Statements, appropriate statements from a logical analysis, okay? Appropriate statements from a logical analysis, and also, so it deals with how to determine the particular symbols to use in that logical analysis, and also how to write those symbols, okay? And there are different symbols of showing things, okay? Like a self-driving car should be able to deduce a person, a pedestrian, by a particular symbol, okay? A pedestrian by a particular symbol, a symbol like somebody, just a sketch of a person, the way you normally sketch a person, right? A sketch of a person, that is a symbol. There are other symbols that a self-driving car should be able to know this symbol represents something. Like for instance, a shape of a bread, a packet of bread. It should be able to know that particular shape, which is it can be a parallelogram, yeah. It can know that that is a bus. If it is a shorter parallelogram, that is a mini bus. If it is a a parallelogram with a big gap at the rear, that's a lorry or that's a truck. So those are symbols, okay? So logical representation is representing these particular rules, right? And they can be in form of syntax or semantics. Semantics are basically the rules by which we can interpret the sentence logic, and it involves assigning a meaning to each sentence. So if there is a symbol like a parallelogram, a full long parallelogram, it is supposed to know that that is a bus. So bus is a semantic, okay? Bus is a semantic, all right? Then there are some advantage, or let's look at advantages of logical representation. I want you to just pass this. I included this for your knowledge, but I don't think it's worth discussing for now. What you have to know is syntax and semantics, because that is what you're going to be asked and tested, okay? So advantages of logical representation. Why should we represent logical data? Rules. The first one is that rules help us to reason, and also rules help us not to pass some certain parameters. So rules help the agent not to pass some certain parameters, meaning that it will always optimize its performance around a particular situation. It will not go further or beyond, okay? And what that does is that it helps to the agent to focus on the particular problem without addressing other problems that are non-related, because rules are like boundaries. Okay, so if it knows that from this symbol this is a bus, it can know nothing else from that. It will be knowing that's a bus. Every time it using its cameras, it sees a bus in its memory, it's going to project that particular symbol and read it as a bus. Okay, so basically it helps it to stay within its course of problem. It will not go further or beyond. Okay, but the disadvantages is the restrictions. All right, and it is challenging to work with those rules in dynamic environments. That's one of the biggest disadvantages. It's challenging to work with those rules in dynamic environments. And what that means is that if 5 years to come, buses will be taking a different shape. But probably in 10 years to come, buses will be taking another very, very different shape. So it will not be knowing that as a bus. You see that? So that's the problem about logical representation, is that in dynamic environments where things change, these rules may not apply. Okay, where things change, these rules may not apply in those kinds of futures. I was watching a video where Elon Musk was featuring, and it's basically about the kind of world that he wants to create. And one of the things that he wants to revolutionize is the transport industry, and he has a company called the Boring Company. Now he was giving some chances, some alternatives of what can be done to reduce traffic on the roads and to use the land mass that is used by roads for more buildings, so that we don't have to have roads on the land. We will have roads underneath. Well, he's revolutionizing that. He's working on that. But one of the solutions he was giving is that one of the ways, if the tunnels will not be enough, or it will be too dangerous to create a lot of tunnels underground, the issue of weakening the ground, such kind of things. But he was saying that the solution to that is having a public buses, which they are like trains, but the thing about them is that underneath them another car can pass through, because we know that buses are normally slow compared to other cars and other vehicles like the motorbikes and the smaller cars. So buses and trucks are very, very, very sometimes slow. Yeah, so that's why they are the ones that cause traffic jams and all those kinds of things. So instead of having cars or buses that buses and trucks that touch the road completely at the bottom part, we will raise the bottom part such that other cars can actually pass through trucks. So on a road, when a bus is moving, other cars can overtake underneath. Now that's very, very it's very, very creative. All right, instead of overtaking from the side, they can actually be overtaken underneath. And that's very, very creative, which means that even accidents will be accidents that are normally which involve buses or trucks and smaller cars can be reduced. Okay, because cars will not be hitting two buses, or will not be hitting buses or hitting lorries. They will be passing under, and it is very safe. Okay, they will be overtaking from under. Okay, so basically that is a very creative solution. That's a very, very creative solution. So what I'm trying to drive at is that is a dynamic environment, because in the future, if that particular idea takes shape, buses will not look the way buses look now. All right, so if a self-driving car right now knows this as a bus, all right, this particular symbol represents a bus. In the next coming future, we need to represent other symbols. You see that? So there's a restriction. It's challenging to work with in dynamic environments. Okay, we need to represent different symbols to represent different things in particular times. Okay, yeah, so that is it about logical representation. Then semantic network representation. Semantic network representation is basically representing what kind of knowledge? Relationship knowledge. And relationship knowledge is what kind of knowledge? Relationship knowledge is, let's see here, it's structural knowledge. So that's why I was saying that these KR formalisms are directly related to the knowledge, to the types of knowledge, right? So a semantic network representation is representing relationship knowledge, all right? And relationship knowledge is this kind of knowledge which you can describe, as we discussed in the object-oriented system analysis and design. Is our relationships a kind of relationships, all right? So it's where this is where not representing knowledge that the agent can use to form generalizations and specializations. Okay, generalizations and specializations. Let's look at a statement like Jerry is a cat, Jerry is a mammal, Jerry is owned by Prior, Jerry is brown colored, all mammals are animals. That's basically number 5 is basically a conclusion from this. If Jerry is a cat and Jerry is a mammal, we can say that all cats are mammals. Okay, so that's a basically, and we are going to look at that when we discuss inductive reasoning and deductive reasoning. Okay, in KRR, inductive reasoning and deductive reasoning, where we make such kind of relationships. Jerry is a cat, Jerry is a mammal, therefore all cats are mammals. Okay, or we can say it rains on Tuesdays. It rains on Tuesdays. And this is the second Tuesday of July. Therefore, all Julys are rainy. Yeah. That's a kind of a generalization. All right. So basically, generalizations and specializations are normally possible by representing semantic network representation. Semantic networks are basically relationship networks which the agent can expand as it looks for a solution. Okay, an agent can expand that network as it looks for a solution through, you remember, generalization and specialization. We form the kinds of inheritance and relationships. Okay. And so you can see here, can you see this kind of relationship? So Jerry is white in color, Jerry is owned by Prior, Jerry is a cat. Therefore, if Jerry is a cat and cat are mammals and a mammal is an animal, therefore Jerry is it's a mammal, right? And Jerry is also an animal, because you can see how that relationship goes. Okay, so it's basically things to do with generalizations and specializations. Now, what are the advantages? The advantages of semantics is that it is a natural representation of knowledge. I can see we have less than 10 minutes remaining, but I'm going to, okay, after this, I'm going to close the class. Then we continue in the next class. But anyway, so let's just finish up this. Semantic networks are basically a natural representation of knowledge. They are natural in nature, because Jerry is a cat, cat is a mammal, and a mammal is a kind of an animal. So Jerry is a mammal, and Jerry is also an animal. That's a very, very natural representation of knowledge. Also, it conveys meaning in a transparent manner. There are no hidden meanings. There are no hidden meanings. They are open. If Jerry is a cat and a cat is a mammal and a mammal is an animal, therefore Jerry is a mammal. Very transparent. Okay. And also these networks are simple and easily understandable. I think that's self-explanatory. It is simple and easily understandable. Even as you can see from this structure, this particular kind of structure is very, very simple and understandable. And however much you infer, however much you increase the relationship downwards, as long as you show the arrows and indicate, then those kinds of That's what you call what we call semantic network relationship. They are very, very easy to understand, and however much you increase, you can still be able to understand it. Okay. And frame representation is representing, now frame is like the opposite of semantic network. Now in semantic network, we understand concepts by looking at their relationships, generalization and specialization. But frame representation is where data is tabulated. Instead of using relationships, we use records like a database. All right. Data is tabulated into frames. Frames are basically records. So frame representation is representing data in form of tables. Okay. And those tables have records and fields, just like a database. Okay. So I want you to see this example. We have slots and filters: title, artificial intelligence; genre, computer science; author, Peter Novick; edition, third edition; year, 1996; page, 1152. Yeah. So can you see these? There are basically fields and records. What are the fields? Title, genre, author, edition, year, and page. Those are the fields. And then artificial intelligence, computer system. These are the different records in those particular fields. Just like database, just as you did, I think you did advanced database systems, or even basic database, introduction to database using MS Access. Yeah, you remember that? Even before you go to database. For database, what did you use? You used Oracle. I think you used Oracle. Suffice it to say, frame representation is where we use tables, just as in a database, to represent the knowledge. Our data tables, and tables are made up of records and fields. Okay. Now the advantages. What time? How much time are we remaining? We have less than 6 minutes anyway. The advantages of frame representation is that grouping of data is very easy. And that is an advantage of tables. That's why MS Excel and MS Access makes for very good data analytics. Okay, because it uses tables. You can even query. All right. And it's also flexible and can be used by many applications in AI. Yeah, it is very flexible and can be used by many applications. It is very easy to add slots, because if you want to add a record, you just add a record. You add, like, you remember the SQL statements for creating new records. Yeah, like there was create table students, right? Create row these into table students. You remember those kinds of things? So it is very easy to add slots, right? To new for new attributes. Or new attributes are basically data for new attributes. And also you can query for missing values. You can search for missing values. You can query. You remember querying a database, searching or filtering. You can search for what you want, and you can also know what is missing, because all data is arranged in tables, rows and columns, records and fields. So you're able to know what is missing and represent it, because it's a table, it is visible. Okay. You are able to run it using a command prompt, and you're able to see the contents of every field and the contents of every record, and you're able to know what is missing, and then you're able to add that particular knowledge, all right, into that particular slot. A slot is an intersection, what you call a cell in Excel and Access. A cell is basically an intersection between a row and a column, or a record and a field. A row and a column. It's called a slot, all right, where a particular data set is contained. And also it is easy to understand and visualize, right? You can just know these are field for types of cars. These are field for car registrations. These are field for car models. These are field for rate of speed of that car, average speed of that car. Now I'm talking about a self-driving car. So if you represent those kinds of knowledge to it in form of table, so that it can understand all the kinds of cars in its environment, then, and if they are in a table, then that is a frame representation, and it is easy to understand. Okay, it's easy to understand because these are tables, rows and columns. This row represents something, this column represents something. Very, very easy to understand and visualize. And even so, that means it's easy to correct. Okay, it is easy to correct. And of course, the disadvantages is that if we are dealing with voluminous information, we cannot easily process such tables. Imagine if we are dealing with a self-driving car where we are supposed to represent other 1,000 types of cars. Not unless we are dealing with a software that generates that table automatically, then we should enter those tables using a command prompt or SQL statements for 1,000 records. So can you see it's not very easy to be processed or to be induced, okay? And also it has a much generalized approach. It doesn't have specifics. It doesn't have specifics. And then what are production rules? Production rules are conditional statements. We have moved from number 3, frame representation. And then now we are now at number 4. We have 2 minutes remaining. Production rules. Production rules are basically conditional statements. And conditional statements normally go like this: while condition, then action. If condition returns true, then action. Else returns false, then action. Those are what we call production rules. So production rules are basically conditional statements. All right, and that's a KR formalism. Like if we are dealing with a self-driving car, if a car is at bus stop and bus arrives, then action, get into the bus. So the self-driving bus should do what? Should open the vehicle. If at station and there are passengers, then open door. If passengers are fully in and the number of passengers in the car is full, then close door, continue journey. All right, so those are basically if or conditional statements. Okay, the advantage of that, and we have less than 1 minute, but let's see if we can finish. The advantage of that is that it is expressed in natural language. And natural language here, we are talking about natural programming language, if statements. Okay, and the production rules are highly modular. Modular meaning that different conditions test for different things. Okay, different conditions test for different things. So you have an if statement to measure the speed of another car coming. You have an if statement to measure if a passenger has successfully entered in or they are still at the door, so that you cannot hit them with the door as it closes, So they are very, very modular. Every if or every conditional statement addresses a particular thing. Let me create another session so that we can finish, and then you can probably ask questions. So let me create another session.